Hi, this is Mrs. Mays. Today we're going to talk about the discovery of the electron. In 1897, J.J. Thomson was messing around with some cathode ray tubes. Cathode ray tubes basically are empty evacuated tubes of glass. So that means there's no air inside. All the air's been removed, so it's a vacuum. And then they put a positive charge on one end and a negative charge on the other. And then these particles flow in between. And the streams of particles, Thomson discovered, were negatively charged. They came from the cathode ray tubes, and that's what led J.J. Thomson to conclude that all elements had these negatively charged particles embedded in their atoms. So here's how he learned that the particles were negatively charged. First, he took a magnet and put it near the cathode ray tube. And he found that when you put one end of the magnet towards the tube, it pushes the particles away. But if you put the opposite end, the north side, then it moves the particles towards the magnet. So remember, opposites attract and like charges repel. So knowing which end of the magnet he'd placed near the cathode ray tube, he was able to deduce that these particles inside there are indeed negatively charged particles. So now that we know there's something that's negative inside the atom, we had to make a suggestion of where these particles might be located. And that's when they came up with what's known as the Plum pudding model. Back in those days, plum pudding was a nice little treat, like a dessert. Now we would maybe refer to this as the chocolate chip cookie model. Oh, if I could spell chocolate. Because the idea is that there's some positive charge in the atom, and it's just this blob of mush that's all positively charged. And then sprinkled through the atom would be these negative charges embedded in the mush of positive charge. So that was the first proposal about where these electrons might be located. We're going to learn some more details about where electrons are later, but at least at this time, in 1904, it was the best description that could explain the observations they found. So it featured a positive sphere of matter with a positive sphere of matter with negative electrons embedded in it. Then a little later, Millikan was doing an experiment to discover the charge of the single electron. If finding the mass could help them learn the charge, finding the charge could help them learn the mass. It turns out discovering the charge was simply easier to measure than the mass of a single electron because they're so very tiny. But what he did is he took an atomizer, kind of like a perfume spray bottle, and sprayed a very fine mist of oils across electrically charged plate. So it formed an electrical field, and then the idea was to sort of get the oil particle to hover inside there or levitate in there, and they could measure the charge that was going through there based on how it moved. So here's some data from Millikan's experiment. In the trials that he did, that are listed here, he found they were associated with charges that all had a common denominator. There was a number they had in common. This is called the least common multiple, I think. So what was the thing that all of these had in common? A number that would go into 4.8. So I'm going to make my math easier because decimals can confuse me sometimes. So we'll call that 48 and 32 and 64 and 96. And we need a number that goes into all of these numbers evenly. So 2 goes, 4 goes. What's the biggest number? The biggest number, oh, I have all my math terms. It's called the greatest common factor. Yeah, now my math terms are coming back to me. So we're looking for the greatest common factor among all of these. Did you find it yet? All of these numbers are divisible by 16. And so when we write this in decimal form, that would be 1.6 times 10 to the negative 19 coulombs. The conclusion Millikan came to is that this must be the charge of a single electron, because there was never any number that he could calculate for the charge where it was not a multiple of the 1.6 times 10 to the negative 19 coulombs. Amazing, right? So currently, the accepted value for the charge of an electron is 1.602 times 10 to the negative 19 coulombs. We got more significant digits in our measurement in this number just because we had better instruments later on so that we could measure with more accuracy and with more precision. So this value for the charge of an electron is typically written with the cursive E, and you'll see this used in your notes and in the problems. But knowing the charge then allowed us to calculate the mass of an electron. We can't weigh it directly because we don't have a scale that's small enough, but the mass of an electron was determined to be 9.11 times 10 to the negative 31 kilograms. That's incredibly small, and we don't have a balance that can weigh things that tiny. So now I have a question for you. Let's look at these charges, A, B, C, and D, and decide which could be the actual charge of an object. Charges are generated when electrons are transferred. So as the electrons are transferred, every time you move one electron, then you would get 1.6 times 10 to the negative 19 coulombs. What if you moved 2 electrons? Then how much would it be? Yeah, twice as much, right? And then if you moved 3 electrons, it would be 3 times as much, and so on. So which of these in our list could actually be the charge of an object? Well, we know it can't be A because that's half of an electron, and that doesn't exist, right? 0.8 is half of 1.6, so that can't be, right? And then 2.0, that's not a multiple of 1.6. That can't be right. 3.2, well, 16 goes into 32 2 times, right? And so maybe this one is it. That might be it, but let's check the last one. 4.0, 16 goes into 48 3 times, but it doesn't go into 4 evenly, so that can't be it. Our best choice is C, 3.2 times 10 to the negative 19 coulombs. Now let's see how well does the Thomson model match reality. Okay, so we have a hydrogen atom in our box, and we're going to shoot some photons in it, and we want to show the spectrum so that we can see what sort of a pattern does it make as we bombard the hydrogen atom with particles of light. We looked at this in our class too, so this should look familiar. We're going to have to let this run for about 60 seconds so that our spectrum can build up. Okay, so now our spectrum down here in the bottom corner is built up, and we can see what types of energy transitions have occurred. So let's look and see. A lot of collisions have occurred with ultraviolet frequencies, some with purple and blue, turquoise, red, and infrared. So these are the collisions that we're observing when we look at a real hydrogen atom bombarded with light particles. Now let's look at the prediction from the Thomson theory. That would be the Plum pudding model. So you can see the positive charge, the red, has a negatively charged electron embedded inside it. That's the blue particle. And some collisions cause it to sort of bounce around, right? But since there's only one energy level in the Thomson model, let's slow this down so you can watch it more closely. Some collisions in the Thomson model don't cause any transition at all, and there's only one energy level, so it looks like there's only one type of energy that causes the electron to move around. So the energy transitions for the electron only occur in the ultraviolet. The problem is, if your theory does not match with reality, we don't get to change reality. We have to revise our theory instead. So the Plum pudding model was a step in the right direction. At least it included the particle known as the electron, which was negatively charged, but it wasn't placed in the right spot yet. So we had to know a little bit more about it. And in the next couple of podcasts, we're going to talk more about where the electron is, especially in Unit 2. We'll locate the electron, any electron, for any element. And you guys will be experts at that by then. So we'll work more on this in class. I'll see you guys later.